Okay, well, this is it's Monday, it's week 3, and we have a midterm exam coming up on Wednesday, so that's just in 2 days. So today I will cover chapter 6, and chapter 6 will appear on the midterm exam. So I know that's relatively quick, but I hope I do a decent job of covering the material, and you'll be able to practice tonight and tomorrow as well. I've also posted this file, practice problems for the midterm exam, and I've got some practice problems for basically chapters 2 through 6, and so you have that. The midterm exam will also have a lot of these questions are kind of calculation based, but the midterm exam will also have some conceptual questions. So that's all in there as well. Okay. Did anyone have any questions before we get started? Midterm exam is in person. It's going to be in the classroom that we normally meet. And yeah, I will provide the bubble in forms. It will be multiple choice, but I'll provide it the bubble in forms and the questions. And I guess when we sit down, I'm going to ask everybody to kind of space themselves out. I think I'll have to go and check the classroom and see exactly how many seats there are and stuff. But I think there's probably enough for everybody to leave like 3 spaces between them, 3 empty seats between them and their neighbors. But I'll just double check, and I'll announce kind of rules regarding seating on the day of the midterm exam. Yeah, it'll happen during normal lecture time. So it'll be Wednesday at 9 a.m. and we will meet in person. I'll be there. Okay. And if some of you have accommodations via CAE, I will get in touch with you there. Oh, okay. Yes, the exam is open notes, and so yeah, you will have to print out your notes. Yeah, I can't let you use your computers or tablets or phones for your source of notes. Yeah, it's got to be paper notes. Yeah, I guess here I'll make a page with some of these rules there. But yeah, thank you for that question. Okay, let's go ahead and take a look at today's lecture. And I also need reference tables. Okay. Okay. All right. So today we will take a look at probability distributions. All right. So again, kind of the big picture here is that we want to make conclusions from data. And in order to do that, we need to be able to distinguish between actual phenomena and random coincidence. And in order to understand what is random coincidence, or what could be random coincidence, we have to learn probability. Okay, and we introduced some of the basic rules of probability in chapter 5. That was last week, and today we're going to expand on that. We're going to introduce this concept of the probability distribution. And this will help us answer questions or situations or scenarios like this, where we are asking, is the carnival game a scam? And so in this scenario, we have this wheel that you spin, half of the spaces are marked lose, half of them are marked win, and there's different prizes on these things, okay? And our friend plays the game 10 times and wins only 3 times. And he comes back and he says, I think the game is a scam, okay? And it's true, if the game were truly fair, we would expect to win about half the time. And if we play 10 times, we would expect to win 5 times out of 10. And our friend only won 3 times, and that's less than 5. So does that mean that the game is a scam? Or is it possible that the game is actually fair and our friend was just unlucky? It was just kind of by random coincidence that our friend had this kind of unfortunate outcome of winning only 3 times out of 10 rather than 5 times out of 10. And so what we will learn today in kind of our lecture on probability distributions is that we'll learn how to figure out the probability associated with the outcome that our friend experienced. Okay, so a probability distribution, and we're going to cover kind of the idea of just probability distributions in general, and then we will also look specifically at 2 types of probability distributions. One is the binomial distribution, and the other is the normal distribution. So a probability distribution describes the probabilities that a random variable can take on, okay? And meanwhile, a random variable is the numeric outcome of a random trial, okay? And so, last week when we were talking about the probabilities of events, we said you can have random events and, we can talk about the outcome of those random events. And we can say, okay, you flip a coin and the coin can land heads. You roll a die and the die could land on the number 5. Or, we could say, we picked a person at random from the classroom and this person was a second-year student. Or I don't know, we had all kinds of things, right? We pick a random person from Texas and this person drives a car. So we had random events and outcomes, okay? A random variable is the outcome to a random event like that, except the outcome has to be a number, okay? It has to be a number, it has to be recorded as a number. What's the difference between dice and die? Dice is the plural of die. So you have 1 die, and then if you have 2 of them, you have 2 dice. So that's that. A random variable is we have random trials, but the outcome has to be a number. The outcome has to be a number for it to be a random variable. And some of these numbers might be more likely than others. It's also possible that all of the outcomes are equally likely, but in a lot of scenarios, some numbers are more probable than others. And a probability distribution shows us the probabilities associated with those possible outcomes. So some outcomes are more likely, the probability distribution will display that. And so we can have probability distributions and we can show them with tables or graphs. I guess with a graph, you might also have a mathematical formula, but overall probability distributions, we can represent them with tables or a graph, okay? So a simple example of a probability distribution is, let's say we've got a die and we roll it and we can get the sides 1 through 6, right? It can land 1 through 6, and each of those sides have equal probability. And this works as a random variable because the outcome is a number, right? The outcome, what's the number that the die landed on? That's the outcome. The outcome's a number. So so we can list off the different possible outcomes. We can say X is the random variable. X can take on the values 1, 2, 3, 4, 5, or 6. and the probability that x takes on the value 1 is 1/6, or the probability that x takes on the value 2 is 1/6, so on and so forth. All of these outcomes have probability 1/6. So this would be the table that represents the probability distribution. It's not very interesting because all of the outcomes are equally likely. So we just write 1/6 for all of these. Okay. We can also represent this with a graph. This graph is also not very interesting, but I have the outcomes that we can get 1, 2, 3, 4, 5, 6. And at each of these outcomes I can get, I have a line, and the height of that line is 1/6. Okay. So 1/6 is around 0.1667. So the height of all of these lines is around 1/6. And that's the probability distribution for rolling a die. Not too fancy then. Okay, so here's another example, very simple. We're gonna flip a coin. Okay. Now, normally when we flip a coin, we think of the outcome as the coin landed heads or the coin landed tails. Okay. And if we were to leave the outcome as the coin landed heads or the coin landed tails, this would not work as a random variable, because a random variable, the what do you call it? The outcome has to be a number, right? For it to be a random variable, the outcome has to be a number. So what we're going to do is we're going to shift kind of the question. We're going to say, how many times did heads appear after one coin flip? Okay, so I'm going to flip the coin once, and instead of saying, did it land heads or did it land tails, I'm going to ask the question, how many heads appeared after one coin flip? And now my answers are going to be, well, it's I saw 0 heads, or I had 1 head, right? If it lands tails, then we're going to say the random variable is 0. And if the coin lands heads, then the random variable is 1. And that's fine, okay? And that works because now we have a number, okay? We have a number and it makes sense. And now I have a probability distribution, and I can say the random variable x can take the value 0 with probability 0.5. The random variable 1, x can take the probability 1 or value 1 with probability 0.5. Okay, so flipping a coin, we don't often think of the outcome of a coin flip as numeric, but you kind of change the question a little bit, and now it is numeric, and we can list off these probabilities. Okay, the probability table itself not too fascinating with values 0.5 and 0.5, but that's fine. Okay, and then here's the graphic display here. 0 with a height 0.5 and 1 with a height of 0.5. Okay, here we can say what are the outcomes when we flip a coin twice? Okay, what if I take the coin and I flip it twice? Okay, when I flip it twice, there are a few different things that could happen. Okay, I can get heads, I can get heads, tails, I can get tails, heads, or tails, tails. Okay, now I cannot create a random variable for these outcomes because these are not numeric outcomes. And so what I have to do is I have to kind of change the outcomes and basically pose a question that corresponds to our coin flip outcomes, and it's a numeric outcome, right? So one thing I can do is I can ask, well, how many times do we get heads after 2 coin flips? How many times do we get heads after 2 coin flips? And this is not going to have a one-to-one mapping, okay? Because here I can say we got heads twice, and that corresponds only to this outcome, heads, heads. I can say heads, we got heads 1 time, and both of these outcomes get mapped, or is part of that answer, that heads appeared once. And then, this one will be heads appeared 0 times, okay? I can't just say, okay, well, this one's going to be, outcome 1, and this is outcome 2, and this is outcome 3, and this is outcome 4. I can't just number these outcomes, because numbering the outcomes, well, if you number the outcomes, there should be some kind of numeric meaning, right? And so if you say this is outcome 1, and this is outcome 2, and outcome 3, and this is outcome 4, someone could ask, why did you choose this to be outcome 2 and this to be outcome 3, and not the other way around? Why not this outcome 2 and why not this outcome 3? Or what is the meaning of getting 2.5? Okay, and we don't have an answer for that. Okay, we don't have an answer for that. So so it has to be a numeric outcome. And so something like, how many times did heads appear? That makes sense, because we can say, okay, we counted and we got heads 0 times here. We counted and we got heads twice here. We counted and we got heads once here. And you can get an answer like 1.5 heads by saying, well, on average, I might get 1.5 heads or something like that, right? On the average of however many pointers. Okay, well, anyway, we can use the rules of probability to figure out the probability of each of these outcomes. And we can say, okay, what's the probability of tails, tails? And we do 0.5 times 0.5, and we get 0.25. And what's the probability of heads, heads? And we also get 0.25. And then what's the probability of heads, tails, or tails, heads? And, we do all of those multiplications, and we get 0.5. And therefore, my probability table has the outcomes 0, 1, and 2. And we get the probability, we get 0 with probability 1/4. We get 1 with probability 1/2. We get 2 with probability 1/4. Okay. And this is what our probability table looks like here. And graphically, it might look like this. I've got a line at 0 with height of 0.25, a line at 1 with a height of 0.5, and a line at 2 with a height of 0.25. Okay, so the outcomes don't all have to be like evenly spaced out. So all of the other examples we've had, the outcomes were 1, 2, 3, 4, 5, 6, or 0, 1, or 0, 1, 2. They don't all have to be evenly spaced out. You can have outcomes that are kind of spaced out a little bit differently. And so let's imagine this prize wheel at the beginning here. Let's say, you have loser spaces, okay? 6 of these spaces are marked lose, and 6 of them are marked win, but the prizes are different. So 5 of the spaces that are winners, you get like the small prize or the medium, and then only 1 of the spaces is marked the large prize. And you say, okay, well, how do we make this numeric, right? So, because if we use the outcomes lose, small prize, and big prize, this doesn't work, because these are categorical outcomes: lose, small prize, and big prize. Those are non-numeric. Those are categorical outcomes. And so, again, for it to be a random variable, the outcome has to be a number. So is there a way we can turn this into a number? And so, one possible way to turn this into a number is we can say, okay, what is the cash value or the dollar value of the outcome, right? So if you lose your prize, what you get is worth $0, right? You get nothing back in return. Whereas maybe the small prize, as I don't know, a small stuffed animal or something, and maybe the value of that product is $1.50 or something like that, right? So we can say the small prize has a value of $1.50, and then the big prize maybe is a bigger stuffed animal, or I don't know, the soccer ball or something, I don't know. Okay, and maybe it has a prize value of $6. Okay, so So we can do this, and now this counts as a numeric variable because now we have numeric outcomes here. Okay, so we can't leave it as categorical values. We have to make sure everything's a numeric variable, a numeric value, in order for it to be a random variable. Okay, and so what's the probability of each of these things? Okay, well, 0, you get the loser spots are 6 out of the 12. So that's a probability 1/2. Okay, small prize, which has a value of $1.50, 5 out of the 12 spaces. And then the big prize, which has a value of $6, has a probability of 1 out of 12. And that's the answer there. Okay, so that's a probability distribution, and it might look like this. So 0 with a height of 0.5, 1.5 with a height of 5/12 is like 0.41, 416 or something, and then 1/12, 0.083. It shows up at 6 has a height of 1/12 here. Okay, all of the examples that I've shown you so far are what we call discrete random variables. Okay, discrete means you're able to list them off. Okay, if you're able to list the probability outcomes of the table, that random variable is discrete. Now, you might have an infinitely discrete random variable, meaning there's infinitely many values that you can get, but even then you can still like at least start a list, I should say. Okay, so if the but on the other hand, if your random variable can take on decimal values that that can't be listed, like if I say give me all the whole numbers from 1 to 10, you can do that. But if I say give me all of the numbers from 1 through 10, you cannot list them, right? There's infinitely many values between 1 and 10. You got 1, but then you also have 1.1 and 1.01 and 1.001 and 1.0001, and you can have infinitely many decimals, and it's just not possible to list them off. And so if you have a variable like that, that would be a continuous random variable, and you won't have a table of probabilities. So for continuous random variables, we represent them with like a mathematical equation called the density, or we can just represent them graphically using kind of a curve or a line. And as far as our class goes, we're only going to just look at the graphs, and we're not going to worry about the mathematical equations. Although if you were to study more statistics, then you'll start looking at the mathematical equations, or if you take a course on probability, you'll probably do that. Okay, so examples. So other examples of random variables, we've already seen some, but we can say I'm going to select a person at random, and I'm going to write down how many siblings this person has. Okay, how many siblings does this person have? And we can list off the possible outcomes that we can get. We can pick someone and we say, how many siblings do you have? And they say, I have 0 siblings. Or they can say, oh, I've got 1 sibling, or I've got 2, or I've got 3, or I come from a big family and I have 7 siblings, or something like that, right? But even then, you can list off all of the values, okay? And the variable there, it's a discrete variable, okay? Because we can list them off. We can say another random variable, though, would be I'm going to pick a person at random. So again, that's the random part. And what the value that we're going to write down is we're going to write down the person's height measured in centimeters. So we're going to say, okay, well, how tall is this person in centimeters? And let's say we had a very precise measuring tool. We can have them stand, and we bring the ruler down on top of their head, and somebody could be 180.0 centimeters tall, Somebody could be 180.01, 180.0127, and there's infinitely many values that we can get for someone's height. You know, we're really only limited by the precision of our measurement tool. Maybe our tool can only record to the nearest, you know, 1/10 of a millimeter or something, right? So, you know, 180, and then this would be 0 millimeters, and this is 1/10 of like this is really tiny. That's still a very precise thing, but anyway, this variable is continuous. This variable would be continuous. Here's another example of a continuous random variable, and we can, and I do this because this one is very very simple, but we can just say, let's say there's a bus stop, and a bus arrives at this bus stop exactly every 12 minutes. Okay, so of course real life isn't like this because sometimes you have to wait longer or whatever. But let's say the bus arrives at the bus stop at a random time, and we are going to the variable will be how long the person has to wait until the next bus. Okay, and so this random variable can be anywhere between 0 and 12, right? The person can arrive just as the bus arrives, like they arrive at the exact same time, and so the person's wait time is 0. Okay, and the person could arrive just as the bus is leaving, so they have to wait 12 minutes for the next bus to arrive. All right, and then the person can arrive anywhere in between. It can have decimals. All of the values between 0 and 12 will have equal probability. And to show that all of the values between 0 and 12 have equal probability, when we draw our graph, we just draw a flat line. Okay, flat line. The height of the line represents its probability, or kind of relative probability, or formally it's known as its density. And it will look like this. Values from 0 to 12 will have the same probability. It's flat. Okay. Values below 0, it's not possible to have any wait time less than 0, so that will have a probability of 0. And then again, assuming our bus arrives exactly every 12 minutes, it's not possible to wait longer than 12 minutes. And so we will have a probability of 0. And that's what our wait time distribution, probability distribution looks like. Okay, if you have a discrete, so this is just a couple rules. If you have a discrete random variable, all of the probabilities must add up to 1. Okay, all of the probabilities must always be positive. So if you kind of look back at some of these tables, if you add these probabilities, they always add up to 1. Okay, if you add these numbers up, they always add up to 1. Okay, if you have a continuous variable, then when you look at this thing, the area in this underneath the curve, we call it area underneath the curve. Here it's a flat line, but basically the area between the x-axis and whatever shape this kind of carves out, that total area will equal 1. Okay, and then again, this line has to be always positive, or at least non-negative. Okay, so it can be 0, but it can never be negative. And the area always has to be 1. Okay. Let me go ahead and give you your first view quiz answer. Today's first view quiz answer for week 3 Monday is the letter A. A as in apple. A as in apple is your first view quiz answer. A as in apple. Okay, all right. So I'm going to continue on here, and let me introduce the binomial distribution. Okay, the binomial distribution is a special case of a random variable. It's a discrete random variable, and it applies to these situations. So all of these conditions, or this, for you to use the binomial distribution, it has to kind of meet all of these specifications. And if it does, then you can do the binomial distribution and you can apply the binomial distribution formula. Okay. So the idea here is you are going to repeat a random trial, say n times. So it's going to be something like, I'm going to flip the coin 5 times. I'm going to roll the die 6 times. I'm going to, I don't know, reach into the, I don't know, bag of marbles or something, and I'm going to do this 12 times. Okay, you're going to do the same thing, same random thing. You're going to do it n times. And anytime you do one of these things, there either something happens or it doesn't. Okay, there's only kind of 2 outcomes, right? So something happens or it doesn't. We traditionally label these things as success versus a failure. That's kind of the traditional labels for the outcomes, but the success isn't necessarily a good thing. Failure isn't necessarily a bad thing. Okay, it could just be something completely neutral, like I'm going to flip the coin 7 times, and we need to, we're going to count how many times it landed heads. Okay, and we can say heads is the success, and it either landed heads or it doesn't. Okay, we could reach into a bowl of M&M candies, and the M&M candies, you have different colors, red and yellow and blue and green and brown, and I don't remember the colors of the M&Ms, but here, if you're going to do binomial, it's either you can't track all of these different colors. You have to say, I either got a red piece of candy or I did not. Okay, and you just pick one of those colors and you say either I got that thing happened, or it did not. Okay, so we say either I got a red piece, success, or I did not, failure. Okay, but it could also, it doesn't have to be necessarily good nor bad, or it could be the opposite, right? You can say, we're going to randomly pick 100 people on campus, and we're going to give them a COVID test or something, and somebody either tests positive or they don't. Okay, and in that case, testing positive would be the quote unquote success. That feels very strange to say that, but basically we're just saying either something happens or it doesn't. Okay, now for it to be a binomial distribution, though, each trial must be independent of the others. So the what do you call it? So that the outcome of one thing is not going to be associated with the outcome of any of the others, right? So coin flips are independent, right? Rolling a die is independent of all other dice rolls. If you pick someone at random, okay, you have to make sure you're not also going to pick like that person's brother or the person standing next to them or something, because then that's not independent, right? Because the person's brother is likely to have similar outcomes. Even the person standing next to someone is likely to be a little bit more similar than someone that's completely random, right? Because people tend to hang out with their friends, and you're more likely, if you pick 2 people who are standing next to each other, they're more likely to have some kind of connection than 2 complete random people, right? And kind of going along with that, every trial must have the same probability of success, so that whenever if you flip the coin, the outcome, the probability that the coin lands heads has to remain the same throughout. Okay, if you're picking a piece of candy out of the bowl, okay, once you pick a piece of candy, you kind of have to put it back. Otherwise, the number of candies remaining in the bowl will change, and the probabilities will also change. Okay, maybe that's a little bit weird, but like if you think of a deck of cards, the very first card you draw, there's 52 cards, 26 red and 26 black, and the very first card you draw, 20 probability of 1/2 of getting red, because there's 26 red, 26 black, 26 out of 52 are red. But let's say that first card you draw is red. Now there's only 51 cards left in the deck, and 25 are red and 26 are black. And now the probability of drawing a red card again is a little bit different. Okay, it's a little bit different. So, so in order for the binomial distribution to apply, once you draw that red card, you have to put it back in the deck so that there's always 52 cards. Okay, and the thing that we are interested in when we are doing a binomial distribution is the number of successes. Okay, so we're doing something n times and we want to know the number of successes. Okay, one moment, please. I got a message on my phone that I need to respond to a little bit. So just one moment, okay? Okay, sorry, thank you for that. Okay, all right, so let's try out an example. 4 flips. We're gonna flip the coin 4 times, and we want to know what is the probability that the coin lands heads exactly 1 time. Okay, now in order to just make this make the numbers easier to kind of follow, we're going to say the probability that it lands heads is not 50-50, it's not 0.5, but the probability it lands heads is 0.7. Okay, so we've got some kind of special coin. It lands heads with probability 0.7. It lands tails, or it doesn't land heads, with probability 0.3. We're going to flip the coin 4 times. And we're going to say all these coin flips are independent of each other. And the question is, what is the probability we get heads exactly 1 time? Okay, so this is a binomial situation, and we will learn the formula, the binomial formula, to answer this question. But I kind of want to solve this using kind of the classical rules of probability first, okay, that we've learned. So you are actually able to answer this question, but it requires you to list off all of the possible outcomes here. We have to list off all of the possible ways we can get exactly 4 heads. I mean, sorry, 4 flips and 1 head. Okay, so we're going to do 4 flips, 1 head. What are the possible ways? Okay, so 4 flips, 1 head. Okay, so the possible ways are we can get heads on the first flip, and that means the remaining flips, there's 3 of them, have to be tails, tails, tails. Okay, we can also get tails on the first flip, heads on the second, tails, tails. We can get this sequence, tails, tails, heads, tails, and tails, 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 heads. Okay, and again, we said the probability of heads is 0.7. The probability of tails is 0.3. And last week, in chapter 5, we learned that sequences of independent events, we can find the probability of that sequence by multiplying all of those probabilities together, right? So all of these events, all of these flips are independent. So we can say this is going to be the probability of heads times the probability of tails times the probability of tails times the probability of tails. And so I'm going to get 0.7 times 0.3 to the third power. Okay. And if we look at this one, we're also going to get I'm going to get tails, 0.3, times probability of heads, 0.7, times the probability of tails, 0.3, times the probability of tails, 0.3. Okay. And, with multiplication, you can rearrange all of them and you get the same value. And so you get 0.7 times 0.3 to the third. And all 4 of these sequences have the exact same probability, 0.7 times 0.3 to the third, 0.7 times 0.3 to the third. Okay, and so the total probability, okay, what's the probability of getting this or this or this or this? That is going to be the sum of all of these things because they're all mutually exclusive. There's no overlap for us to worry about. Okay, so probability of get basically 4 flips with 1 head is going to equal, all things have the probability of 0.7 times 0.3 to the third power, and there's four of them, so I'm going to have 4 times 0.7 times 0.3 to the third. Okay, and this there's something here, 4 times 0.7 times 0.3 to the third power. That is 0.0756. Okay. Is that good? Does that make sense? So I think I wrote that down. 4 times 0.7 times 0.3 to the third, 0.0756. Okay. What if we do this? We're going to do the same question, except this time we're going to say, what is the probability we get heads exactly 2 times? We're going to flip the coin 4 times. Probability of heads is 0.7. Probability of tails is 0.3. This time we want to know what's the probability I get heads 2 times. 2 times. Okay. So there are 6 possible arrangements. I can get heads on the first 2 flips, and get heads on the first, then tails, and then heads. I can get heads and then tails, and then heads. Okay. I can also get this. All right, and this is all of the possible arrangements. Okay, so we now have 6 possible arrangements. Okay, what is the probability for any one of these arrangements? You can enter it in the chat if you're following along. What's the probability of any one of these arrangements? So, and probability of heads, there's a probability of heads, times the probability of tails, times the probability of tails. And yeah, we would get 0.7 squared times 0.3 squared. And exactly, that's 0.0441. Okay, so yeah, you guys got it in the chat. 0.7 squared times 0.3 squared. We get 0.0441. And so the total probability of all of this is going to be 6, right? So the total probability of all arrangements will be 6 times 0.7 squared times 0.3 squared. And so if I take this and I multiply it by 6, that's 0.2646. Okay, so there you go. And that's the answer. Okay, great. Okay, so if we wanted to kind of generalize this into a formula, we would say, you know, if we looked at, if I go back a couple of slides to saying getting 1 head and 4 flips, we said, well, it was 4 times 0.7 times 0.3 to the third. And I could just say, well, okay, 4 is the number of arrangements. And then 0.7 is, you know, what's the probability of getting heads, okay, or a success? And how many times do I need to get heads? Well, we need to get it 1 time, so I raise it to the first power. What's the probability of not getting heads, or the probability of a failure? That's going to be 0.3, and that needs to happen 3 times, so I raise it to the third power, okay? And this pattern here applies for the other scenario as well. So when we said this answer is 6 times 0.7 squared times 0.3 squared, well, we said, you know, any one of those arrangements was the probability of success 0.7 squared times the probability of failure 0.3 squared, because we need to get two heads and 2 tails. And the total probability with all 6 arrangements, you take that and you multiply by the number of arrangements. So using kind of, so we might ask, well, how do we figure out the number of arrangements? Okay. What I did was I just listed them off, right? I just said, okay, well, there's 4 ways to get heads 1 time out of 4 flips, and there's 6 ways to get heads twice and stuff. We can use this formula. This is called the binomial coefficient, okay? And this will give us all of the possible arrangements that you have, you know, and this is helpful when you have big numbers, right? If I said, hey, let's, how many ways are there to get 5 heads and 10 flips, or how many ways are there to get 4 heads and 10 flips? That would be a lot of ways to have to arrange or write them out, and it just wouldn't be practical. So we can use this formula, the binomial coefficient, and the way we read it is, you know, you see the n and the k inside this parentheses. It's called, we read this as n choose k, n choose k. And this is how many ways are there to arrange a sequence of n trials where you're going to have k successes. And the formula is given by n factorial divided by k factorial times n minus k quantity factorial. Factorial is just all of the integers, all of the whole numbers from 1 to that value multiplied together. So 4 factorial is 4 times 3 times 2 times 1, and you get 24. So when we said, okay, how many ways are there to have 4 flips where you get 2 heads? That would be 4 choose 2, and you would get 24 on the numerator. 2 factorial is 2 times 1, so that's just 2. 4 minus 2 quantity is 2, so you have 2 factorial on the bottom. So you have 24 divided by 4, and you get 6. You have something like 10 trials and 4 successes. Then you have 10 choose 4, and you would do 10 factorial divided by 4 factorial times 6 factorial, okay? This becomes, you know, a bit of work to do. Your calculator might have an NCR button. On mine, I would do 10, and I do shift divide for this NCR. 10 choose 4, and I get 210, okay? I get 210. You can do this in R, and you can do choose 10, 4, and you get 210. You can go to on the internet, and you can just type in 10 choose 4 into your search engine, and it will probably come back and say, oh, it's 210. And you can probably do some, pretty big numbers. 50, choose 20. Okay, and that, you get some ridiculous number. This is on the magnitude of 10 to the 13th power times 4.7. So, okay, so this is much too big, but that's 50, choose 20. Okay, I don't know, is this able to do it? Choose 50, comma 20. Yeah, it gives me, okay, same number, just way too many combinations there. So that's how we do this. Okay. So if we want to do this, and we'll use formula letters instead, we will take the number of arrangements and say that's n choose x. The probability of success is p. And how many successes do we want? We want x of those. Okay, so we're going to do p raised to the x. And then what are these numbers over here? Well, this is the probability of not getting a success, or probability of failure. So we do 1 minus p. And then if we have a total of n trials and x of them are successes, then the number of failures we have has to be n minus x. Okay. And so, this would just be exactly n choose x is 6. P is 0.7. We wanted 2 successes, so p 0.7 squared. And 1 minus p is the probability of getting tails, 0.3, and it needed to happen 2 times. So we raise that to the 2nd power, and we get 0.2646. Okay. And on R, you can also use this formula or this function called dbinom. Dbinom. You say, well, you give it the x, we want to know 2 successes out of 4 trials, and the probability of success each time is 0.7. And when you enter that, you get the exact same number, 0.2646. And if you say, well, what's the probability I get 1? Okay, 1, we get 0.0756, which is what we found earlier too. Okay, so that's the binomial probability. So let's try an example. So I enjoy watching NBA, and Steph Curry plays for the Golden State Warriors and is perhaps one of, if not the greatest shooter of all time, one of the greatest shooters of all time. And he has a very, very high free throw percentage, meaning every time if you keep track of how many free throws he's thrown and how many he's made 92.6%, which is very, very, very good. Okay. And so, I just said, let's pretend he's going to take 5 free throws in a game. Okay. So he takes 5 of them, and we're going to ask, what is the probability he misses 1? What's the probability he misses? We'll say exactly 1 free throw. So one thing here is we have to assume this is a binomial situation, meaning we have to assume each of the free throws are independent of the others, and maybe that's not a good assumption. Okay, maybe the probability of making a free throw is not constant throughout, but let's just kind of pretend. And so notice the way this question is phrased. It says, what's the probability he misses 1? Okay. And so we have to ask, well, what is our x here? X being the number of successes, right? So if P is the probability of a success, probability of making it, what does it mean for your x to be here? Okay. So in this scenario, let's identify the different values that we have. We need to have our n, we need to have our p, we need to figure out our x. So n, it says we're going to take 5 free throws, so n is 5. Okay, p is given to us, 0.926. It says the probability he makes a free throw at any of these is going to be 0.926. Okay, missing 1 means x has to be 4, right? This is and miss one shot. Miss one shot means makes 4. Okay, so so x here is going to be 4. All right, our formula is n choose x, p to the x, 1 minus p to the n minus x. So we're going to have 5 choose 4, 0.926 to the 4, and 1 minus 0.926 to the 5 minus 4, which is 1. Okay. And, this is just a matter of plugging it into your calculator. And it turns out the answer you get is 0.2720. 0.2720 here. Okay. So far, so good. Okay, I hope so. Let me go ahead and give you your second view quiz answer. Your second view quiz answer is B. B as in binomial, or B as in bear. B. B is your second view quiz answer, the letter B. Okay, do we feel okay about binomial? Any questions? All right, so let's revisit this problem here. And we said a carnival game has a wheel divided in 12 spaces. Half of them are lose, half are correspond to some kind of prize. Our friend plays 10 games and he only wins 3 games. And he says, I think this is a scam, right? He said, I feel like I should have won 5. I should have won 5 out of the 5 out of the 10, and I only won 3. Okay, so does winning only 3 out of 10 games indicate that the game is a scam? Or is it possible that the game is actually fair and just kind of by random coincidence, our friend had this unfortunate outcome? So to kind of ask, well, we could ask, what is the probability that someone would win only 3 times or less? Okay, if the game were fair. If the game were fair, is it possible for someone to just win only 3 times by bad luck? So we want to know what's the probability that could happen. Okay, and we're going to look up 3 or less, because if our friend accused the game of being a scam for winning only 3 times, he would also accuse the game of being a scam if he only won 2 times or only 1 time, or if he won 0 times out of 10. I think if he won 0 times out of 10, he'd be very upset. But he won 3 times, and he was upset about that, so he would accuse 3, 2, 1, or 0. So let's ask, what's the probability that it would look like the game is a scam according to our friend? So the answer here is, this is a binomial problem where we're playing the game 10 times. The probability of winning, if we assume the game were fair every time we win, is 0.5. And we would be upset if we won only 0 times. We would be upset if we won only 1 time. We would be upset if we only won 2 times. And our friend's still upset even though he won 3 times. Okay. And so we can say, okay, well, how often would it appear if our definition of the game's a scam is you win only 3 times or less? How often does it appear like the game's a scam, just even though it's a fair game? And so we can do this, and I can go through the calculations, but I can just ask R, give me D binom, how many 3 wins out of 10 games, where each game is 0.5, assuming it's fair. That happens with 11 probability. This one happens with about 4%. And this one happens with, less than 1%. And, getting 0 wins out of 10 games is very low probability, but it's not impossible. Okay. It happens, less than 1 in 10,000, 1 in 1,000, but it's not impossible. Okay. So even if the game is actually fair, there's still a 17% probability that just kind of by bad luck, somebody wins only 3 games out of 10. So So I don't know. I'm not convinced that the game's a scam, right? Just it could be. It could have just been you were one of the unlucky 17% of people where this kind of thing happens. Okay. On the other hand, if our friend only won one game out of 10, right? He played the game 10 times and he wins only one game out of 10, we can say, okay, what's the probability that you would get only one win out of 10 games or 0 wins, okay? And that happens with it could happen, right? It's not impossible. Even if it's a fair game, like if you're flipping a coin, even if it's a fair coin, just by bad luck, it's possible that the coin lands heads only one time out of 10 flips. But how often does it happen? Okay, it's not impossible, but it happens only about 1% of the time. So if you play the game 10 times and you win only one time out of 10, okay, you do the calculations and it comes back and says, oh, this could happen, it's not impossible, but it happens only 1% of the time. I think in that scenario, you'd say, well, maybe I was just one of the really unlucky 1%, or maybe an easier explanation is the game is a scam. And it's not that I just happen to be the unlucky 1%, but rather, nah, the game's a scam. And that's why I got this low probability outcome. Okay. But here, getting 3 wins out of 10 happens with a 17% probability. I'm not convinced. I mean, the game could be a scam, and that's why he only won 3 games out of 10. But it's not impossible for it to be a fair game, and he was just part of the unlucky 17%. 17% is not that low, right? It's not huge, but it's not that low. Okay, well, anyway, we'll come back to that later. This is kind of the logic that we use in hypothesis testing. This is an exercise that I made up, but I will skip it. You can do this on your own time, okay? Admission rate at a university is 16%. I think admission rates for UCLA just came out for like fall. It was like 8.5% admission rate, which is it's like, wow, it's getting really tough to get in. But I'm grateful. I'm very grateful to teach here at UCLA, because truly I feel like I'm working with really the best students. So thank you for coming to UCLA. Thank you for enrolling and taking my class. And yeah, I'm very grateful to be able to teach you as students. I don't have to worry about you. Like, are you going to study for the midterm? Like, I know that you guys will, because again, you're at UCLA. You are in that top 8%. So anyway, the mean and standard deviation of a binomial distribution. So sometimes we want to know certain values about our probability distributions, and we can say, what is the mean of a binomial distribution? So the idea here is, I said, let's, if I flip the coin 4 times, what's the probability I get heads twice? Or what's the probability I get heads 1 time, or something like that, okay? The mean here is saying, well, if you flip the coin 4 times, what is the average number of heads that you would get, okay? So sometimes you would get 2 heads, sometimes you get 3 heads, sometimes you get 1 head. Every time, if you flip the coin 4 times. And the idea is, if you repeated this millions of times, flipping the coin 4 times and counting how many heads you get, then what is the average? What's the average outcome? Okay, that's the mean of a binomial distribution. And I think this answer makes intuitive sense. The answer is going to be n times p. The number you expect is going to be your number of trials multiplied by the probability of success. Okay, and you just do n times p and you get your answer. That's basically why our friend said I expected to win 5 games out of when I played the carnival game 10 times, I expected to win 5 times because if the game is fair, probability is 0.5. If we're playing 10 times, we're expecting on average to win 5 out of 10. He only won 3. That's why he was upset. Okay, standard deviation is this formula. This is a little bit less intuitive, and I don't want to get into the explanation for it. So just jot this down in your notes. If you're ever asked what's the standard deviation of the binomial distribution, the answer is the square root of n times p times 1 minus p. Okay, we're going to move on, and we're going to now introduce the normal distribution. So the normal distribution is a very important probability distribution, and it will form the foundation for a lot of our statistical inference in the future. The normal distribution is a continuous distribution. It is unimodal, it is symmetric, and being continuous, we represent the distribution with a curve rather than some kind of table or listing out the outcomes. And so this curve looks like this. Sometimes we call this the bell curve, but because it looks like, if you could imagine, I don't know, putting a handle on, can I draw? Okay, never mind, I'm not gonna draw, but put a handle right here, and you could, it's like one of those big church bells or something. Okay, but this is what it looks like, and the idea here is values near the middle. So this one is centered at 0. We're going to say values near the middle show up frequently. Okay, this is near average, and as you go above average, you get fewer. Okay, as you go below average, you get fewer. The curve goes down, and as you get far above average, the curve gets really low and close to 0. So as you go above, say, 2, okay, now the probability of that is quite low. And as you go above 3, it's really low. And as you go above 4, it's like practically 0. Same thing going on the opposite side. As you go down below -2 or -3, it gets lower and lower and lower, close to 0. Okay, so values that are much higher than the center or much lower than the center show up much less frequently. Okay, and important idea is it's a probability distribution. So if you were to shade the whole thing in, calculate the area underneath, area inside this curve, the total area is equal to 1. Total area is equal to 1. So we have, so we're going to start off with what we call the standard normal distribution. This is also called the Z distribution. Okay, the Z distribution has a mean of 0 and has a standard deviation of 1. Okay, mean of 0 and standard deviation of 1. And it's a continuous distribution, and this is a little bit strange to think about. But the normal distribution, the probability of getting any one exact value is 0. So the probability of getting exactly the value 1.2277895 is 0. Okay. We can talk about, what's the probability of getting, within, 1/100th of some number, but the probability of getting an exact value, because if you think of an exact value, there's infinitely many decimal places after it, and the probability of getting any one exact value is 0. So anyway, let's just look at this picture. I say, what's the probability that Z ends up being less than 0? Okay, so if we're centered at 0, and I say, what's the probability we're going to be less than 0? Okay, well, the total area is 1. So if I draw a thing here, and if I say, okay, we're centered at 0, and we're gonna shade everything to the left of 0 over here. How much have I shaded this area? What is this area? Well, this area is equal to 0.5, right? So, oh, yeah, so symbolically, we would say this area, what's the probability that z is less than 0 is equal to that area, and that's going to be 0.5. Okay, on the flip side, what if I say, what's the probability that z is greater than or equal to 0, right? So I'm going to kind of flip this around, and we're going to say, okay, what's this area over here? Okay, so here, where this is going to be, what's the probability that z is greater than or equal to 0? Okay, so that's this area. In this area, well, if the total area is 1, we're going to do area 1 minus 0.5. We'll also get 0.5. So this is, we have 0.5 over on this side. I'm going to have 0.5 over on this side. So this answer is also 0.5. I'm going to do 1 minus the complement probability that z is less than 0, and I get 0.5. Okay. So we have this thing called the empirical rule, and let me see if I can zoom in here. All right. So this diagram. So this shows us the normal distribution. And the concept here is that if I shade in, if the total area here is 100%, okay, and I shade in between z equal to 1 and -1, this area here, this is approximately from 1 to -1, we get about 68%, okay? And then if I go from what color to use here? If I go from here to here, okay, we're going to get about 95%. So from z equal to 2 to -2, we get around 95%. Okay, and then finally, if I go all the way out to z equal to 3 and -3, we're going to get almost everything. And this is not quite 100%. You can see the tiniest little piece out here, but we get almost everything, 0.997, okay? And if you go to 4 and -4, it's going to be even closer to 100%, but you could zoom in here and there would be even just the tiniest bit of a sliver here, okay, as you go further and further out, okay? So so all we're saying is if we look at our z-scores, most of our values have z's between 1 and -1, around over, about 2/3, a little over 2/3 of z's between 1 and -1. And then, the vast majority, all right, about 95%, only around 1 in 20 have z-scores above 2 or below -2. And then almost everything, okay, only a few extreme values are above z equal to 3 or z equal to -3. So do you remember z-scores from back in chapter 3, which is how many standard deviations we are from the mean? That's what we're applying here, okay? So if you have a normal distribution, you can calculate your z-score, how many standard deviations we are from the mean, and we have this, okay? And that kind of gives us a guideline, and we would say z greater than 2 or z less than -2, this is considered unusual. And z greater than 3 or z more negative than -3 would be highly unusual. I guess I can do less than or equal to, greater than or equal to 2, greater than or equal to 3, okay? Highly unusual. So if you get a z-score 3 or more, you'd say, ooh, this is very unusual, okay? Z-scores of 2 or more would be considered unusual, okay? Because this is around 1 in 20. And this is around 3 in 1,000. Okay, so very around, it's about how rare those things are. Okay, approximately what proportion have z greater than 1? Approximately what proportion have z greater than 1? Well, the diagram here, so if we draw this, okay, we said, well, this is 1 and this is -1. We said we get around 0.68 in here, okay? So if I have around 68% in here, that means in total, here and here, we're gonna have around 32%, right? And if I only want this half, okay, so the upper half will be half of that, okay? So about 0.16 is above x equal to 1, okay? 0.16 is above x equal to 1. So that's going to be our answer here. Z greater than 1, about 0.16. So if we know 68% are between 1 and -1, we got 32% outside of that, and around 16% will be above positive 1. Okay, what if we have this number like 0.42? Okay, well, 0.42, that's not 1, 2, or 3. So how do we deal with this? Okay, so here's kind of our picture. Here's this picture here. And so here I've got 0, and 0.42 is just a little bit over that. Okay, how much do I have shaded to the left? How much do I have shaded to the left? 0.42. So this is kind of this is my picture here. And I got 0, and I'm going to draw a line at 0.42, and I want to shade everything to the left here. And I want to know what is this area? Okay, so this area. So to answer this, we have to use a reference table. Okay, and so on Canvas, I have uploaded this table. You'll need this, reference tables. I guess I will include, let's see. Yeah, it comes with this binomial. We don't need this, but I will include the standard normal, the first 2 pages of this on your midterm exam. Okay, but you can print out your own too if you want. But I will include the first 2 pages, standard normal, cumulative probabilities. I'll include this on the midterm exam. Okay, so the way it works is this table always gives you the area to the left of z, right? So it shows you kind of the diagram. Here's z and the shaded area to the left. And so this is kind of where we are. We're on the positive side. There's a negative side where z can be negative values. And then there's a positive side where z can be positive values. And we are at z equal to 0.42. Okay, so we want to know what is the probability. If we look at this picture, we want to know what's the probability that z is less than or equal to 0.42. And so what we'll do is we'll go to the table and we go to the row 0.4 and we'll go to the column 0.02, right? Because if you add those two together, you'll get 0.42, right? So we go to the row 0.4 and the column 0.02, and the number here is 0.6628. Okay, so this and that's our answer, 0.6628. We go to the row 0.4 and the column 0.02. So I think I highlighted this. You go to the row 0.4 and the column 0.02, and that's going to be your number. That's going to be the number. The table always gives you the area to the left. Okay. You can also use R. You can say, well, there's the function here is p norm. You put in the z-score, and it says, oh, you know, your area is 0.66275773. So R is able to give you a little bit more precision. I mean, we're going to write 0.6628. That's close enough. Okay. So always remember that the table, or if you use R and you use p norm, it's always going to give you the area to the left of z. If you want the area to the right of z, you have to take that number and you subtract it from 1. So if I said, what's the area? What is the probability that z is greater than 0.42? We would do 1 minus 0.6628. So it would be 1 minus the area to the left of z. And I would get 0.3372. 0.3372. So that's just 1 minus 0.6628. I think maybe the diagram makes it easier to see. You know, what's this area? Well, yeah, that makes sense. And this area is over 0.6628. This is going to be 1 minus 0.6628. Okay, so that's going to be 0.3372. Okay, simple enough, simple enough. All right, why don't you try a couple exercises here. I just want to make sure you guys can use your normal table. And okay, so take a minute here and make sure you download this standard normal table from Canvas. Okay, all right, so take a minute, try this out. I think you guys can use it just fine. But I'll give you a few seconds. Figure this out. All right, what'd you guys get for z less than negative 1.4? Okay, so for this, I would look up, yeah, exactly. We would look up negative 1.4, the row negative 1.4 and the column 0.00. And the answer is 0.0808, 0.0808. Yep, negative 1.400, right? Okay, and then negative 1.04. I'll go to the row negative 1.0 and the column 0.04. Negative 1.04, area to the left of that is 0.1492. 0.1492. So here, let me just draw this one. So here is 0, and here is negative 1.04, and I get 0.1492. The area to the left of that probability that z is less than negative 1.04. 0.1492. Okay, and then all right, what about the other side? We're gonna come over here, and now we got positive 1.04, and this time we want to know what's the area to the right of this. Okay, what's the area to the right? So I can go to the table and I can look up positive 1.04. Positive 1.04 is 0.8, gives me 0.8508, right? So the table always gives you the area to the left. So this says 0.8508 from the table, right? Table gives area to the left. Positive 1.04. Okay, so the area to the right, we would do 1 minus 0.8508. And we also get 0.1492. Okay, and so the area to the left of negative 1.04 and the area to the right of positive 1.04 are both 0.1492. All right, here with more precisions. Decimal places here I use p norm, but yeah. Okay, and so this, because the normal distribution is symmetric, the area to the right of any z value is equal to the area to the left of the negative of that z value. So the area to the left of negative 1.04 is equal to the area to the right of positive 1.04. So that could be a potentially useful shortcut, anytime you're doing some calculations and stuff. All right, let's try generalizing the normal distribution. So far we've been working with a standard normal, but here we can use kind of z-scores and get values here, right? So here are some slightly made up numbers just for simplicity, but we'll say in the United States, the height of adult men is approximately normal, right? So the true normal distribution, it's hard to find something exactly normal, but we're going to pretend that heights of men in the US are approximately normal. And so, and the mean is 69.5 and the standard deviation is 3. And so this is kind of a shorthand way of saying there's a normal distribution. So we're going to say height comes from a normal distribution. So this is like a shorthand way of saying this. And we're going to say the mean, mu is 69.5, and the standard deviation of this is 3 inches. And now the question is, what proportion of men are shorter than 72? Okay, so we want to know what proportion of men are shorter than 6 feet tall. Okay, so I'm going to put 69.5 and draw 72, and we want to know what is this area over here? Okay, what is this area? Okay, so the way we're going to answer this is we're going to convert, we have the standard normal table, so we're going to convert everything to z-scores, okay? So 69.5, we're going to convert to 0. This is the mean. This is going to be z equal to 0. And we want to convert 72 to a z-score. Z equals something, okay? So what is the z-score for 72? Well, z-score, if you remember, was x minus the mean divided by the standard deviation, right? Z-score is distance from the mean and standard deviations. So we're going to say, okay, well, our z-score is 72 minus 69.5 divided by 3, right? So 72 is 2.5 inches above the mean. And each standard deviation is 3. So we're not quite one whole standard deviation above the mean. So I do 2.5 divided by 3. And we see, okay, we're 5/6 or 0.83 standard deviations. Whoops, 0.83 standard deviations above the mean. So this corresponds to a z-score of 0.83. Okay, so if we were one standard deviation above the mean, that would be 72.5. But here we're only, 0.83 of a standard deviation. We're at 72. Okay, does that kind of make sense? Converting the question into z-score. So the question of what is the probability that someone's height is less than 72? This is equivalent to asking what's the probability that z is less than 0.83. Okay, and now that I've turned it into a z-score, I can go to the reference table, and I'm going to look up z equal to 0.83. Oh, too much. All right, 0.8, column 0.03, 0.7967, 0.7967. So this is equal from the table 0.7967. Look up and the table and get 0.7967. So I think I've done this work for you here on this slide. So you convert it to a z-score and then you look it up in the table. Okay. Why don't you try this example? And when you get your answer, give me a thumbs up. Give me a thumbs up on Zoom. So try this out. Take a minute here and try out this example. Okay, so you guys worked through this. Maybe some of you are still working. So the idea here, again, we're going to put in the center, we're going to put the mean, 69.5. And this time we're asking what proportion of adult men are shorter than 71 inches. So here I've got 71, and we want to know, okay, what is the area? What's this area over here? Okay. Well, we're going to first calculate our z-score, and we're going to say, okay, well, 71, so 69.5 becomes z equal to 0. 71, what is this z-score going to be? Okay, it's going to be 71 minus 69.5 divided by 3. Well, 71 is 1.5 inches above the mean. And if each standard deviation is 3 inches, we're half a standard deviation. So our z-score is going to be 0.5. So now I just go to the z table and I'm going to look up z equal to 0.5. Z equal to 0.5. So I go to the row 0.5 and the column 0.50, and I get 0.6915. Okay, so I go to the row 0.5, column 0.00 on the table, and the area to the left, 0.6915. That's our answer. So we're about 69% have heights less than 71 inches. That's our answer. Okay. What is the probability that a randomly chosen adult male has a height between 71 and 72 inches? Okay. So this one, I didn't write the slide answer here. The question says, okay, what is the probability? This is terrible depiction here. Okay. All right, so in the center, I've got 69.5. And then I got a line at 71 and a line at 72. And the question is asking, what is the probability that someone's height is between 71 and 72 inches? What is the probability that 71 is less than someone's height, which is less than 72. Okay, so how do we get this? How do we get this? Okay, well, I'm going to say this area is equal to, first we're going to find um, 72, and we're going to take the area to the left, and I'm going to do minus everything to the left of 71. Okay, so I'm going to have this minus this. Okay, so if I do area to the left of 72, probability height is less than 72 minus probability that height is less than 71, then I will be given the area in between. The area in between. Okay, so from the previous slides, we found, okay, well, what is the probability that someone's shorter than 72? We were 0.7967. Right, so this answer was 0.7967, 0.7967. And what's the probability that someone's shorter than 71? We found this answer to be 0.6915. 0.6915. Okay, which means this slice here has to be the difference between those two areas. This is going to be 0.7967 minus 0.6915, and we're going to get 0.1052. All right, and that's going to be my answer. So this chunk right here is going to be 0.1052. So you can say, what's the area in between two spots? Okay, you find the area to the left of one of those numbers, and then you subtract off the area to the left of the other side. Okay. All right, let me give you your last view quiz answer. Last view quiz answer is the letter B. B as in bear. B as in bear is your last view quiz answer. All right, we've got a few more slides here, and then we'll wrap it up. Okay. Sometimes we work backwards from the normal distribution, and so this is a silly example, but I said, okay, what if we wanted to make a hat, and it's going to fit 96% of people's heads? Okay, so if you want the middle 96%, then you'll go from the 2nd percentile to the 98th percentile. Okay, so you want to kind of make sure you get, the biggest hat will get to the 98th percentile, only 2% won't be able to fit. And then the smallest will be at the 2nd percentile, only 2% won't be able to fit below. So you'll get the middle kind of 96%. All right, I made up some numbers here. Don't fact check me. But we're going to say, let's say the mean head circumference is 23 inches and the standard deviation is 0.8 inches. Okay, so we're going to say head circumference normally distributed, the mean is 23, standard deviation is 0.8. Okay, and the question is, what is the 98th percentile? What is the 98th percentile? So this is how the picture looks. Okay, the idea here is I'm going to draw 23 here, and this time I have a mystery number. I don't know this location, What I do know is that if I shade this in over here, this area is equal to 0.98. And the question is, what value, what x gives me an area of 0.98? Okay, well, first, before we even get there, let's work with z's, right? So if we have z equal to 0, the area to the left is 0.5. And the question is, well, what z gives me 0.98? So first we're going to ask what z gives an area of 0.98, okay? So what is the z that gives 0.98 to the left? So what we have to do is we have to go to the table and we have to look through all of these things, and we're going to find the z-score that gives an area of 0.98. Now, do not look up z equal to 0.98. Okay, don't look up z equal to 0.98 and pick 0.8365. That's the wrong thing to do. Okay, you have to look through all of these numbers and you got to find the number that's closest to 0.9800. Okay, so we go to the z table and we say what is closest to 0.9800. Okay, and I find 0.9798. I find 0.9803. Okay, this one is just a tiny bit closer. Okay, 0.9798. So we're going to go with this one. Okay, 0.9798 is at z equal to 2.05. So this is in the row 2.0 and the column 0.05. So we're going to say z equal to 2.05. Okay, so the probability that z is less than 2.05 is 0.9798, which is pretty close to 98%. Okay, z equal to 0.205. All right, but I'm not done. I need to convert into a head circumference. So to do this, I'm going to just use my z-score formula. X minus the mean over the standard deviation. I plug in the values I have. 2.05 is equal to x minus the mean of 23 divided by 0.8. And now I solve for x. I'm going to have 0.8 times 2.05 is equal to x minus 23. And now I'll have 23 plus 0.8 times 2.05 is 1.64 equal to x. And so I get x is equal to 24.64. And that's going to be my number. This is 24.64. Gives me an area to the left of 0.98. Area to the left of 0.98. So this is the number I find, and I solve. 24.64. Okay, I think I left this as an exercise for you to try out on your own time, and I give you the answer there, so you can work through that. Okay, this is it. That's it for today's lecture. So we'll end here, and have a good rest of your day. I will have office hours starting at 11:30. So maybe I'll see you there. If not, have a great rest of your day. Good luck as you study. Oh, third view quiz answer is the letter B. Letter B is your third view quiz answer. And good luck as you study, and we will see you on Wednesday for the midterm exam. So good luck, everyone, and we will see you on Wednesday.